Chapter number 15, Polymers. Do you think that daily life would have been easier and colorful without the discovery and varied applications of polymers? The use of polymers in a manufacture of plastic buckets, cups and saucers, children's toys, packing bags, synthetic clothing materials, automobile tires, gears and seals, electrically insulating materials and machine parts has completely revolutionized the daily life as well as the industrial scenario. Indeed, the polymers are the backbone of four major industries, that is plastics, elastomers, fibers and paints and varnishes. The word polymer is coined from two Greek words. Poly means many and mer means unit or part. The term polymer is defined as very large molecules having high molecular weight 10⁻³ to 10⁷ unit. These are also referred to as macromolecules, which are formed by joining of repeating structural units on a large scale. Repeating structural units are derived from some simple and reactive molecules known as monomers and are linked to each other by covalent bonds. This process of formation of polymers from respective monomers is called polymerization. Transformation of ethene to polyethene and interaction of hexamethylene diamine and adipic acid leading to the formation of nylon 6,6 are examples of two different types of polymerization reactions. Classification of polymers. There are several ways of classification of polymers based on some special consideration. The following are some of the common classification of polymers. First, classification based on source. Under this type of classification, there are three subcategories. First, natural polymers. These polymers are found in plants and animals. Examples are proteins, cellulose, starch, some resins and rubber. Second, semi-synthetic polymers. Cellulose derivatives as cellulose acetate, rayon and cellulose nitrate, etc. are the usual examples of this subcategory. Third, synthetic polymers. A variety of synthetic polymers as plastic, polythene, synthetic fibers, nylon 6,6 and synthetic rubbers, Buna S are some examples of man-made polymers extensively used in daily life as well as in industries. Second, classification based on structure of polymers. There are three different types based on the structure of polymers. First, linear polymers. These polymers consist of long and straight chains. The examples are high density polythene, polyvinyl fluoride, etc. These are represented as. Second, branch chain polymers. These polymers contain linear chains having some branches. Example, low density polythene. These are depicted as follows. Third, cross-linked or network polymers. These are usually formed from bifunctional or trifunctional monomers and contain strong covalent bonds between various linear polymer chains. Example, bakelite, melamine, etc. These polymers are depicted as follows. Third, classification based on mode of polymerization. Polymers can also be classified on the basis of mode of polymerization into two subgroups. First, addition polymers. The addition polymers are formed by the repeated addition of the monomer molecule possessing double or triple bonds. Example, the formation of polyethene from ethene and polypropene from propane. However, the addition polymers formed by the polymerization of a single monomeric species are known as homopolymers. Example, polyethene. And CH2, double bond CH2 ethene gives CH2 single bond CH2 polyethene. Homopolymer. The polymer made by addition polymerization from two different monomers are termed as copolymers. Example, Buna S, Buna N, etc. Condensation polymers. The condensation polymers are formed by repeated condensation reaction between two different bifunctional or trifunctional monomeric units. In this polymerization reactions, the elimination of small molecules such as water, alcohol, hydrogen chloride, etc. take place. The examples are terylene, dacrin, nylon 6,6, nylon 6, etc. For example, nylon 6,6 is formed by the condensation of hexamethylene diamine with adipic acid. Classification based on molecular forces. A large number of polymer applications in different fields depend on their unique mechanical properties like tensile strength, elasticity, toughness, etc. These mechanical properties are governed by intermolecular forces. Example, van der Waals force and hydrogen bonds present in the polymer. These forces also bind the polymer chains. Under this category, the polymers are classified into the following four subgroups on the basis of magnitude of intermolecular forces present in them. First, elastomers. These are rubber-like solids with elastic properties. In this, Elastomeric polymers, the polymer chains are held together by weakest intermolecular forces. These weak binding forces permit the polymer to be stretched. A few cross links are introduced in between the chains which help the polymer to retract to its original position after the force is released, as in vulcanized rubber. The examples are Buna-S, Buna-N, neoprene, etc. Second, fibers. Fibers are the thread-forming solids which possess high tensile strength and high modulus. These characteristics can be attributed to the strong intermolecular forces like hydrogen bonding. These strong forces also lead to close packing of chains and thus impart crystalline nature. The examples are polyamides, nylon 6,6, polyesters, terylene, etc. Third, thermoplastic polymers. These are the linear or slightly branched long chain molecules capable of repeatedly softening on heating and hardening on cooling. These polymers possesses intermolecular forces of attractions intermediate between elastomers and fibers. Some common thermoplastics are polythene, polystyrene, polyvinyls, etc. Fourth, thermosetting polymers. These polymers are cross-linked or heavily branched molecules which on heating undergo extensive cross-linking in molds and again becomes infusible. This cannot be reused. Some common examples are bakelite, urea, formaldehyde resins, etc. Classification based on growth polymerization. The addition and condensation polymers are nowadays also referred to as chain growth polymers and step growth polymers depending on the type of polymerization mechanism they undergo during their formation. Types of polymerization reactions. There are two broad types of polymerization reactions, that is, the addition or chain growth polymerization and condensation or step growth polymerization. Addition polymerization or chain growth polymerization. In this type of polymerization, the molecules of the same monomer or different monomers add together on a large scale to form a polymer. The monomers used are unsaturated compounds, example alkenes, alkynes and their derivatives. This mode of polymerization leading to an increase in chain length or chain growth can take place through the formation of either free radicals or ionic species. However, the free radical governed addition or chain growth polymerization is the most common mode. Free radical mechanism. A variety of alkenes or dienes and their derivatives are polymerized in the presence of a free radical generating initiator catalyst like benzoyl peroxide, acetyl peroxide, tert-butyl peroxide, etc. For example, the polymerization of ethene to polyethene consists of heating or exposing to a light mixture of ethene with a small amount of benzoyl peroxide initiator. The process starts with the addition of phenyl radical formed by the peroxide to the ethene double bond, thus generating a new and larger free radical. This step is called chain initiating step. As this radical reacts with another molecule of ethene, another bigger sized radical is formed. The repetition of this sequence with new and bigger radicals carries the reaction forward, and the step is termed as chain propagating step. Ultimately, at some stage, the product radical thus formed reacts with another radical to form the polymerized product. This step is called the chain terminating step. The sequence of steps may be depicted as follows. Chain terminating step. For termination of the long chain, these free radicals can combine in different ways to form polyethene. One mode of termination of chain is shown as under. Preparation of some important addition polymers. A. Polyethene. There are two types of polyethene as given below. First, low density polyethene. It is obtained by the polymerization of ethene under high pressure of 1000 to 2000 atmospheres at a temperature of 350 Kelvin to 570 Kelvin in the presence of traces of dioxygen or a peroxide initiator catalyst. The low density polyethene LDP obtained through the free radical addition and H-atom abstraction has highly branched structure. Low density polyethene is chemically inert and tough but flexible and poor conductor of electricity. Hence it is used in the insulation of electricity carrying wires and manufacture of squeeze bottles, toys and flexible pipes. Second, high density polyethene. It is formed when addition polymerization of ethene takes place in a hydrocarbon solvent in the presence of a catalyst such as triethyl aluminium and titanium tetrachloride, Ziegler-Natta Catalyst at a temperature of 333 Kelvin to 343 Kelvin and under a pressure of 6 to 7 atmospheres. High-density polyethylene HDP thus produced consists of linear molecules and has a high density due to close packing. It is also chemically inert and more tough and hard. It is used for manufacturing buckets, dustbins, bottles, pipes, etc. Polytetrafluoroethene Teflon. Teflon is manufactured by heating tetrafluoroethene with a free radical or persulfate catalyst at high pressures. It is chemically inert and resistant to attack by corrosive reagents. It is used in making oil seals and gaskets and also used for non-stick surface coated utensils. It is poor conductor of electricity. Polyacrylonitrile. The addition polymerization of acrylonitrile in the presence of peroxide catalyst lead to the formation of polyacrylonitrile. Polyacrylonitrile is used as a substitute for wool in making commercial fibers as Orlon or acrylion. Condensation polymerization or step growth polymerization. This type of polymerization generally involves a repetitive condensation reaction between two bifunctional monomers. This polycondensation reaction may result in the loss of some simple molecules as water, alcohol, etc. and lead to the formation of high molecular mass condensation polymers. In these reactions, the product of each step is again a bifunctional species and the sequence of condensation goes on. Since each step produces a distinct functionalized species and is independent of each other, this process is also called as step growth polymerization. The formation of pyrrolene or dacron by the interaction of ethylene glycol and terephthalic acid is an example of this type of polymerization. Some important condensation polymerization reactions characterized by their linking units are described below. First, polyamides. These polymers possessing amide linkages are important examples of synthetic fibers and are termed as nylons. The general method of preparation consists of the condensation polymerization of diamides with dicarboxylic acid and also of amino acids and their lectins. Preparation of nylons. First, nylon 6,6. It is prepared by the condensation polymerization of hexamethylene diamine with adipic acid under high pressure and at high temperature. Nylon 6,6 is used in making sheets, bristles for brushes and in textile industry. Nylon 6. It is obtained by heating caprolactam with water at high temperature. Nylon 6 is used for the manufacture of tire cords, fabrics and ropes. Polyesters. These are the polycondensation products of dicarboxylic acids and diols. Dacron or terylene is the best known example of polyesters. It is manufactured by heating a mixture of ethylene glycol and terephthalic acid at 420 to 460 Kelvin in the presence of zinc acetate antimony trioxide catalyst as per the reaction given earlier. Dacron fiber terylene is grease resistant and is used in blending with cotton and wool fibers and also as a glass reinforcing materials in safety helmets, etc. Phenol. Formaldehyde polymer, bakelite and related polymers. Phenol formaldehyde polymers are the oldest synthetic polymers. These are obtained by the condensation reaction of phenol with formaldehyde in the presence of either an acid or a base catalyst. Reaction starts with the initial formation of O and or p-hydroxymethyl phenol derivatives which further react with phenol to form compounds having rings joined to each other through CH2 groups. The initial product could be a linear product. Example, Novolac used in paints. Novolac on heating with formaldehyde undergoes cross-linking to form an infusible solid mass called bakelite. It is used for making combs, phonograph records, electrical switches and handles of various utensils. Fourth, melamine formaldehyde polymer. Melamine formaldehyde polymer is formed by the condensation polymerization of melamine and formaldehyde. It is used in the manufacture of unbreakable crockery. Copolymerization. Copolymerization is a polymerization reaction in which a mixture of more than one monomeric species is allowed to polymerize and form a copolymer. The copolymer can be made not only by chain growth polymerization but by step growth polymerization also. It contains multiple units of each monomer used in the same polymeric chain. For example, a mixture of 1,3-butadiene and styrene can form a copolymer. Copolymers have properties quite different from homopolymers. For example, butadiene styrene copolymer is quite tough and is a good substitute for natural rubber. It is used for manufacture of auto tires, floor tiles, footwear components, cable insulation, etc. Rubber. Natural rubber. Rubber is a natural polymer and possesses elastic properties. It is also termed as elastomer and has variety of uses. It is manufactured from rubber latex, which is colloidal dispersion of rubber in water. This latex is obtained from the bark of rubber tree and is found in India, Sri Lanka, Indonesia, Malaysia and South America. Natural rubber may be considered as a linear polymer of isoprene 2-methyl-1,3-butadiene and is also called as cis-1,4-polyisoprene. The cis-polyisoprene molecule consists of various chains held together by weak van der Waals interaction and has a coiled structure. Thus, it can be stretched like a spring and exhibits elastic properties. Vulcanization of rubber. Natural rubber becomes soft at high temperature, that is more than 335 degree Kelvin, and brittle at low temperatures, that is less than 283 Kelvin, and shows high water absorption capacity. It is soluble in non-polar solvents and is non-resistant to attack by oxidizing agents. To improve upon these physical properties, a process of vulcanization is carried out. This process consists of heating a mixture of raw rubber with sulfur and an appropriate additive at a temperature range between 373 Kelvin to 415 Kelvin. On vulcanization, sulfur forms cross links at the reactive sites of double bonds and thus the rubber gets stiffened. In the manufacture of tire rubber, 5% of sulfur is used as cross-linking agent. The probable structure of vulcanized rubber molecules are depicted below. Synthetic rubbers. Synthetic rubber is any vulcanizable rubber like polymer which is capable of getting stretched to twice its length. However, it returns to its original shape and size as soon as the external stretching force is released. The synthetic rubbers are either homopolymers of 1,3-butadiene derivatives or copolymers of 1,3-butadiene or its derivatives with another unsaturated monomer. Preparation of synthetic rubbers. First, neoprene. Neoprene or polychloroprene is formed by the free radical polymerization of chloroprene. It has superior resistance to vegetable and mineral oils. It is used for manufacturing conveyor belts, gaskets and hoses. Buna N. You have already studied about Buna S in section 15.1.3. Buna N is obtained by the copolymerization of 1,3-butadiene and acrylonitrile in the presence of peroxide catalyst. It is resistant to the action of petrol, lubricating oil and organic solvents. It is used in making oil seals, tank lining, etc. Molecular mass of polymers. Polymer properties are closely related to their molecular mass, size and structure. The growth of the polymer chain during their synthesis is dependent upon the availability of the monomers in the reaction mixture. Thus, the polymer sample contains chains of varying lengths and hence its molecular mass is always expressed as an average. The molecular mass of polymers can be determined by chemical and physical methods. Biodegradable polymers. A large number of polymers are quite resistant to the environmental degradation processes and are thus responsible for the accumulation of polymeric solid waste materials. This solid waste cause acute environmental problems and remain undegraded for quite a long time. In a view of the general awareness and concern for the problem created by the polymeric solid waste, certain new biodegradable synthetic polymers have been designed and developed. These polymers contain functional groups similar to the functional group present in the biopolymers. Aliphatic polyesters are one of the important classes of biodegradable polymers. Some important examples are given below. First, poly-beta-hydroxybutyrate co-beta-hydroxyvalerate (PHBV). It is obtained by the copolymerization of 3-hydroxybutanoic acid and 3-hydroxypentanoic acid. PHBV is used in specialty packaging, orthopedic devices and in controlled release of drugs. PHBV undergoes bacterial degradation in the environment. Second, nylon 2, nylon 6. It is an alternating polyamide copolymer of glycine H2N single bond CH2 single bond COOH and amino caproic acid H2N CH2 whole 5 COOH and is biodegradable. Can you write the structure of this copolymer? Polymers of commercial importance. Besides the polymers already discussed, some other commercially important polymers along with the structures and uses are given below in table 15.1. Name of polymer: polypropane. Monomer: propane. Uses: manufacture of ropes, toys, pipes, fibers, etc. Name of polymer: polystyrene. Monomer: styrene. Uses: as insulator, wrapping material, manufacture of toys, radio and television cabinets. Name of polymer: polyvinyl chloride PVC. Monomer: vinyl chloride. Uses: manufacture of raincoats, handbags, vinyl flooring, water pipes. Name of polymer: urea formaldehyde resin. Monomer: urea and formaldehyde. Uses: for making unbreakable cups and laminated sheets. Name of polymer: glyptal. Monomer: A. ethylene glycol, B. phthalic acid. Uses: manufacture of paints and lacquers. Name of polymers: bakelite. Monomer: phenol formaldehyde. Uses: for making combs, electrical switches, handles of utensils and computer disks. Thanks for watching the video. Please do like, comment, share and subscribe. Some important points for NEET will be